In the course of history, humans usually choose to yield to the destructive power of nature. But on a small island called Jaime, isolated in the middle of the North Atlantic, a different script was written. This is not just the story of a volcanic eruption. It is an epic symphony of engineering courage and a seemingly insane decision using the ocean to stop a river of fire. A battle that lasted 5 months, consumed billions of tons of seawater, and ended with a result that even the most optimistic scientists could not have imagined. Iceland is a land of ice and fire located directly atop the mid-Atlantic ridge, where two massive tectonic plates are slowly drifting apart. Yet the volcano Eldfell on the island of Jaime had remained dormant for nearly 5,900 years. For local residents, it was simply part of a peaceful landscape. In the early hours of January 23, 1973, the ground split open. A fissure more than 2 kilometers long erupted, turning the night sky into a curtain of intense red fire. In less than 6 hours, all 5,300 inhabitants were evacuated quickly thanks to the fishing fleet already anchored in the harbor. But once the people were safe, their most valuable asset, the port of Jaime, was suddenly at risk of disappearing. If lava blocked the harbor entrance, the island's economy and a significant portion of Iceland's gross domestic product would collapse. As basaltic lava heated to around 1,000 degrees advanced toward the port, an unprecedented idea was proposed: cool it and force it to change direction. From a technical standpoint, lava is not a simple liquid. It is molten rock with extremely high viscosity. When it comes into contact with cold water, its surface layer solidifies almost instantly into hard stone. Icelandic engineers realized that if they could create a sufficiently thick rock barrier along the edge of the flow, the pressure from behind would force the lava to rise or divert elsewhere instead of invading the harbor. In other words, they were not trying to extinguish the lava, they were trying to freeze it in a controlled way, just enough to divert a catastrophe. What began as an emergency measure quickly evolved into an industrial-scale operation. Iceland rapidly assembled a system to draw seawater, increase its pressure, route it through a network of pipes, and spray it precisely at critical points to slow and redirect the Eldfell lava. The turning point came in late March when 32 high-pressure pumps arrived from the United States, equipment normally used in extreme oil industry environments. Rather than concentrating all the pumps in a single location and operating them at maximum capacity, engineers organized them into 4 independent sets to increase reliability. Each set functioned like a production line. First, 2 low-pressure pumps drew seawater into an intermediate reservoir, stabilizing the flow and reducing surges. Then 5 to 7 high-pressure pumps pushed the water into a pressurized tank, which fed pipelines leading to the front line. In total, the system used 43 pumps, with combined engine power of around 2,700 kilonewtons, driven by both gasoline and diesel engines. Each set could deliver approximately 800 to 1,000 liters per second, with a pumping head of about 100 meters, pushing water through roughly 1 kilometer of pipeline. But numbers on paper did not always match reality in the field. Many pumps were not designed for continuous seawater operation, leading to a series of battle-like problems: broken rotor shafts, degraded seals, worn valves, and even metal fatigue failures, combined with cavitation and erosion in the suction pumps. In other words, while fighting, the lava engineers also had to constantly adapt and repair the pumping system to prevent total collapse. Over time, the hydraulic challenge intensified. Spray points had to move upward and outward as the lava advanced. As pipelines lengthened, friction losses increased and nozzle pressure dropped. At the same time, the rising terrain demanded greater pumping head. The campaign, therefore, was not about using as much water as possible, but about precisely calculating spray positions so that every liter produced the maximum cooling effect. What shocked most observers was how the system was deployed, dragging and installing pipes directly on top of still living lava, extremely hot and constantly deforming. The ground beneath could sink swell crack or slide stretching pipes beyond their limits and causing ruptures. Dense clouds of steam rose continuously. Radiant heat felt like standing inside an oven. Visibility was poor and operations were brutally difficult. Working conditions resembled a military engineering unit on the front line, where a single mistake could render an entire pipeline useless. Initially, 6-inch aluminum pipes were used because they were quick to assemble and relatively flexible. However, the metal was heavy and rigid, and even small movements in the lava base could damage them. The true breakthrough came with the adoption of high-strength plastic pipes. From mid-March onward, pipes with diameters of 140, 225, and 315 millimeters were introduced. Delivered in 15-meter sections, they were thermally welded into segments of 100 to 200 meters, then connected into longer lines. The total length of the pipeline network exceeded 12 kilometers, most of it composed of plastic pipes. At first glance, placing plastic pipes on incandescent rock seems absurd. In practice, it made perfect sense. The secret lay in the continuous flow of cold water inside the pipes, which acted as an internal cooling system. External heat passed through the pipe walls and was immediately carried away by the water, preventing the plastic from reaching its softening or melting temperature. There were moments when wooden supports ignited and aluminum structures warped from the heat, while the plastic pipes retained their shape thanks to internal cooling. The purpose of spraying water was not to extinguish the lava, but to force it to solidify earlier. When water hit the lava's hot surface, it boiled violently and instantly turned into steam. This process removed enormous amounts of heat, causing the lava surface to rapidly form a solid rock crust. With the crust forming earlier, the lava thickened, flowed more slowly, accumulated more easily, and was forced to change direction instead of advancing straight ahead. Continuous seawater spraying was maintained from late March until July 10, 1973. During that period, approximately 6.2 million tons of seawater were pumped onto the island. One visible side effect was the crystallization of sea salt, which coated vast lava areas in white, an estimated 220,000 tons of salt. This salt layer became both the visual signature of the operation and the source of later problems, such as corrosion scaling and damage to infrastructure surfaces. Then, while everyone anxiously watched to see whether the lava flow would truly stop, a strange phenomenon began to appear. After weeks of continuous seawater spraying, the black lava flow began to change color in an unexpected way. White streaks appeared across the surface from a distance, resembling snow dusted over hot rock. In reality, it was crystallized salt. When seawater contacts lava at extreme temperatures, the liquid portion evaporates almost instantly, while dissolved salt and minerals cannot evaporate and instead crystallize into a white layer. Because spraying occurred on a massive scale and over many days, salt accumulation became enormous, estimated at over 200,000 tons, enough to transform an entire lava field into a stark white wall visible from afar. Remarkably, this salt layer was not merely dust-thin. In areas of intense spraying water flowed briefly over the lava surface before fully evaporating, depositing salt in thick plates and crusts similar to mineral scaling, but on a colossal scale. Visually, the contrast was striking: white salt, black rock, and the glowing orange-red of still-hot fissures. Yet the most important process occurred beneath the surface. Cooling lava typically develops an irregular surface filled with cracks and voids. With continuous high-volume water application, some water infiltrated these fissures beneath the still incandescent crust. There it boiled violently inside the lava mass itself, extracting heat directly from the interior that sustained the flow. As steam formed in confined spaces, pressure increases caused additional microfractures, opening new pathways for water infiltration. A chain reaction followed more cracks, allowed more water in producing more steam, extracting more heat. Lava that was once plastic rapidly became dense and solidified, as if a river of molten mud were freezing into stone. From a flow perspective, these deeply solidified zones became natural anchors. When the front, hardened lava behind it could no longer slide freely, piled up, raised the flow level, and was ultimately forced to seek an easier alternative route. Because lava always follows the path of least resistance, creating just a few strategically placed solidified blocks was enough to slow and divert an entire advancing flow. The white salt layer also became an unintended visual map. Areas with thicker deposits corresponded to concentrated spray zones where lava crust cooled fastest. Viscosity increased and solidification was most likely. In other words, the white wall was both a chemical byproduct of seawater and a visible record of where human intervention had been most intense. This is where the deeper meaning of the story lies. Humans cannot extinguish a volcano, but they can control its consequences through engineering. Seawater was used as a massive heat extraction tool, and the white salt layer became proof of a calculated intervention, cooling the right place at the right time, forcing lava to choose another path. When Eldfell calmed in early July 1973, what impressed people most was not only what had been lost, but what had been created after 5 months of chaos. The lava flow that once threatened to seal the harbor entrance solidified into a massive rock formation extending into the sea, unintentionally becoming a natural breakwater. Thanks to this barrier, Jaime's harbor waters became more sheltered from wind and waves, allowing fishing vessels to enter and exit more safely under various weather conditions. And the gift did not stop there. Lava advancing into the sea added approximately 2.5 square kilometers of new land, increasing the island's area by nearly 20%. From an urban planning perspective, it resembled a massive territorial expansion project carried out by nature itself. Authorities and residents gained new space to reorganize public areas, infrastructure, and construct new facilities. Even volcanic materials such as ash and tephra were reused in foundations, reinforcements, and infrastructure improvements, especially roads and construction zones. The most valuable technological aspect, however, lay in how the lava mass was utilized after surface cooling. Instead of seeing it as a useless field of rocks, Icelanders recognized it as a trapped energy source. Because volcanic rock is a poor heat conductor, the core of lava flows can retain temperatures of several hundred degrees Celsius for many years. Engineers developed a method to extract this residual heat using principles similar to geothermal energy applied to a newly formed reservoir. They installed pipes or shallow wells in still hot areas and circulated water through a heat exchange system. Cold water descended, absorbed heat, and returned as hot water or steam, which transferred energy through heat exchangers to supply heating and hot water to the town. The operation was not simple. Flow rates had to be controlled to prevent thermal shock corrosion from salt, and minerals had to be mitigated, scaling formation limited as water heated, and temperatures continuously monitored as the heat source gradually declined. In return, however, for decades, residual heat from the eruption provided Jaime with low-cost heating, and hot water turning a former lava field into a natural thermal battery serving everyday life. In summary, Eldfell did not merely create a new volcano. It reshaped the entire island. The harbor became more protected territory, expanded significantly, and most importantly, people converted residual heat into a useful energy system. It was a rare outcome in which a natural disaster ended not only with survival, but with long-term advantage. The 1973 Eldfell eruption was not just a natural disaster, it was a lesson in adaptation. By combining sharp technical thinking with extraordinary courage, Icelanders demonstrated that it is not necessary to defeat nature by force, but possible to guide it through intelligence. Today, standing atop Eldfell, one can still feel the gentle warmth rising from within the earth, a silent reminder of a fiery battle in which seawater managed to tame the blood of the planet.